Hi there, welcome to another video from Hegarty Maths. It's Mr. Hegarty here, and in this video we are classifying turning points. So just a reminder of what turning points are and what we've done previously. We talked about turning points on graphs or functions as the point at which the graph turns around. And more precisely, we said that marks where the graph changes from an increasing function to a decreasing function or vice versa, or where the gradient changes sign. And we also said we found turning points, we found where they existed on a curve by solving dy by dx is equal to 0, because at a turning point the gradient is also 0. Now that's all well and good, that's great stuff, but there are ways to classify turning points as well. There are different types of turning points we need to be aware of. And the picture on the following slide just shows two names we need to know. The first turning point on our graph, this one here, we would call a local maximum. And this turning point here on our graph, we would call a local minimum. Now, the reason it's fairly obvious why we might call it a maximum or minimum based on this picture here. You can see that the graph increases to a maximum point, then starts decreasing down here to a minimum point where it just starts increasing again. It's very important though we use the word local, because actually it wouldn't be fair to say that is the maximum point of the whole graph. There's a place over here where the function has a bigger value. So it's a local maximum in that in its close region, it is a maximum. So they're two words we need to know. And when we're finding turning points, we're often going to have to state whether it is a local maximum or local minimum. So the technique we're going to use to classify those is on the following slide. Now, before we look to the right here, let's just for a moment look at the left. What's happening at the first turning point, the one most to the left? Well, it's a local maximum, we can see it visually, but just before that turning point, the gradient is positive because the function is increasing. At the turning point, the gradient is 0. After the turning point, more to the right, the gradient is negative. We go from positive gradient to 0 gradient to negative gradient. That's a maximum or local maximum. What about a local minimum? Well, we go from negative gradient to 0 gradient to positive gradient. That's our local minimum. So the diagram on the right tries to simplify this, and it basically says that if you go from a positive gradient to a 0 gradient to a negative gradient, you must have had a local maximum. And if you go from a negative gradient to a 0 gradient to a positive gradient again, it must be a local minimum. And that's the technique we're going to use, having found our turning points, to actually state whether it's a local maximum or minimum. We're going to work out the gradient function slightly to the left, slightly to the right, and see how the signs change. So let's have a go at that. Here's our first question. Pause and have a go. So here we're asked to find the coordinates of the turning point for the graph y equals x squared, subtract x, add 3. But also we're asked to determine whether the turning point found is a local maximum or local minimum. So the first step of this particular question is like we've done before, finding the coordinate of the turning point. So our function is y equals x squared, subtract x, add 3. Our gradient function, therefore, dy by dx, will be 2x subtract 1, just differentiating there. And to find a turning point, we solve dy by dx is equal to 0. So let's solve that. Let's let 2x subtract 1 equals 0. Add 1 to both sides and divide by 2. You get that x is equal to a half. So the x value is a half. The y value corresponding to that, well, that would be, if I substitute a half into the function, be a half squared, take away a half, add 3. So the y value here, a half squared, is a quarter, take away a half, add 3. And the y value, when you do that, would be 2 3/4, or in an improper fraction form, would be equal to 11 over 4. So the coordinates of the turning point, therefore, are a half and 11 over 4. So, first step done, we have found the coordinates. Next step, however, is to classify the turning point, okay? So, what do we know? We know that the gradient function dy by dx when x is equal to a half is 0. Because this is what we did on the left-hand side here. So we know the gradient function at x is a half is equal to 0. Let's work out the gradient function, its value, slightly to the right of a half. A half is the same as 0.5. So I just go up a little bit. I might go up something like 0.1 to 0.6. When you evaluate the gradient function there, i.e. you substitute 0.6 into this here, i.e. 2 multiplied by 0.6 take away 1, you get the value 0.2. If we work out the value of the gradient function slightly to the left, i.e. at something like x is maybe 0.4, we'd be substituting in to the gradient function and we get an answer of negative 0.2 here. So let's think what's happening. We've got a negative gradient slightly to the left, we've got a 0 gradient at the turning point, and we've got a positive gradient afterwards slightly to the right of the turning point. So this looks like it's a local minimum. So state that at the end, a half 11 over 4 is a local minimum. And highlight that answer so it's clear we have stated our answer and we're done. Next question, pause and have a go. So again, similar idea, asked to find the turning point for this curve and determine whether it is a local maximum or minimum. As we've done before, start by finding the gradient function. So our original function is 13 subtract 2x subtract x squared. Our gradient function, therefore, when we differentiate our original function, will be equal to negative 2 subtract 2x, just differentiating this expression here. To find a turning point, we're solving dy by dx is equal to 0. The gradient function equals 0. So let's let negative 2 subtract 2x equals 0. Add 2 to both sides. Divide both sides by negative 2. And you get x is equal to negative 1. We were asked for the coordinates, so we really need the y coordinates as well. So substituting in back to the original function, that would be 13 subtract 2 brackets negative 1 subtract negative 1 all squared. Just be careful with your negatives here. That's 13. So negative 2 multiplied by negative 1 is positive 2. And negative 1 all squared is 1, so we're subtracting that 1. So y is therefore equal to 14. So our coordinate pair is negative 1, 14 for our turning point. However, we do also have to classify that turning point as a local maximum or a local minimum. So what we're going to do is do what we did before. We know the value of the gradient function dy by dx when x is equal to negative 1 is 0. That's the work we did on the left. So dy by dx, therefore, when x is just a little bit bigger, let's say negative 0.9, that's more to the right on the number line. So we're going to substitute that into our gradient function, which is marked there on the left. So that would be negative 2 subtract 2 multiplied by negative 0.9. And when you do that, you get yourself negative 0.2. Let's work out dy by dx, the gradient function, a little bit to the left. So at x is, let's say, negative 1.1. And when we substitute in there and work out the answer, we get actually positive 0.2. So what's happening here? Well, slightly to the left, we've got a positive gradient. At the turning point, we've got a 0 gradient. Slightly to the right, we've got a negative gradient, and therefore we must have a local maximum. So we can state negative 114 is a local maximum, and we're done. Next question, pause and have a go. So same idea here, find the coordinates of the turning point of the following curve, determine whether the turning point is a local maximum or minimum. So our function is 6 divided by x squared add 12x. Now, if we want to work out the gradient function, it's nice to have everything in nice, neat powers. So let's just rewrite this as 6x to the negative 2 add 12x. Now we're going to differentiate dy by dx. So that's going to end up being, if I do it in steps, bring down that negative 2, keep the 6 there, reduce the power by 1, and 12x just differentiates to 12. So dy by dx here is going to give me negative 12x to the power of negative 3 add 12. And just because I'm going to need to substitute in to the gradient function, I'm just going to rewrite this in fraction form as 12 over x cubed add 12, like that. Now, we were asked to find the coordinates of the turning point. All we've done so far is actually find the gradient function. So we're going to need to solve, actually I'll do it in another column here. We're going to need to solve dy by dx is equal to 0. So let's let negative 12 over x cubed add 12 equals 0. I'm going to add 12 over x cubed to both sides, so I get 12 is equal to 12 over x cubed. Multiply both sides by x cubed to remove the x cubed off the denominator on the right. Get as follows. Divide by 12 and take the cube root. I get myself x is equal to 1. I was asked for the coordinates, so it's very important I find the y coordinate as well. Y is therefore, I'm going to substitute x is 1 back into the original curve, not the gradient function, into the curve, and I would get 6 over 1 squared add 12 multiplied by 1, and I get y is 18. So our coordinates of our turning point are x is 1 and y is 18. So great stuff so far. However, we have not classified that turning point. What do we know? We know dy by dx at x is equal to 1 has value 0 because it's a turning point at x is equal to 1. So we need to work out dy by dx a little bit to the left, maybe at x is 0.9, and we need to work out dy by dx a little bit to the right, maybe at 1.1. So what we're going to do is we're going to substitute in there 6 over 0.9 cubed plus 12 multiplied by 0.9. And over here, substituting in, it would be 6 over 1.1 cubed plus 12 multiplied by 1.1. So in the first case over here, we get something like negative 4.46, etc. We know it's 0 here. And on the right, we would get 2.984, etc. So what do we have? Well, we've got a negative gradient to the left, a 0 gradient at the turning point, and a positive gradient to the right. Very clearly, we can see this must be a local minimum. So 1,18 is a local minimum. And just highlight that so it's clear that was our final answer. And we're done. And that's it for this particular video. Thanks for watching.